The Lewis dot structures that we've been drawing have shown us how the atoms are connected in the molecule, but they don't give us a very good idea of what the 3D image of the molecule is. So we're going to be looking at the VSEPR theory, which is the valence shell electron pair repulsion theory, and it tells us what the geometry of the molecule is. So we're going to be focusing in on the electron pairs around the central atom. So either lone pairs or bonded pairs. That's going to tell us what the geometry is. So the first thing we have to do when we're figuring out the geometry of the molecule is we draw the Lewis dot structure. That way we can see what bonded pairs and what lone pairs are on the central atom. So first we want to look at, again, what's on the central atom. We call these electron domains. So pretty much anything that's on the central atom is an electron domain. So here we have two single bonds, we have a lone pair, and we have a double bond. So all of those things count as one electron domain. So a single bond is one domain, a lone pair, one domain. And even a double bond, it's one domain. So even though there's two bonds, still just counts as one domain. So on number 4, it says to determine the number of electron groups around the central atom in problem 3. So we're just going to do a couple of those here. Okay, so for example, let's do this one. Okay, CO2, so this is G from number 3. So we have this is CO3 negative 2. Okay. So we're only looking at what's around the central atom. So we have 3 domains around the central atom. So each single bond counts as 1, the double bond counts as 1. So a total of 3 domains around carbon. Let's do one more. Let's do let's do SO2. So SO2 looks like this. Okay, so on SO2, there are 3 domains. We have a double bond, which counts as 1, a lone pair counts as 1, and a single bond that counts as 1. So 3 domains total. So we're going to go through the geometries, and we'll look at, again, what's on the central, and it's going to affect based on whether it's bonding or lone pairs. It's going to affect the geometry. So first geometry we're going to do is linear. So for linear geometry, you only have 2 bonding domains on the central atom. So you have to be careful here, because just because you draw something linear does not mean that it's actually linear. So just because I draw a Lewis dot structure linear doesn't mean it's linear. So a great example of that is water. So here's water, and let's look at the example for linear. Okay, CO2. So we know that for linear we have 2 bonding domains. So on CO2, that's what we have. We have 2 double bonds, but again, remember they count as 1. So 2 bonding domains here. So that's linear, but with with water, we have 2 single bonds and 2 lone pairs. So actually we have 4 domains around oxygen and water. So just because I drew that linear in the Lewis dot structure does not mean the actual geometry of water looks like that. Okay, actually looks like this. So we don't get our geometry based on how we drew the Lewis dot structure. We get what's around it from the Lewis dot structure, but not the actual geometry. Okay, next is trigonal planar. So trigonal planar has 3 bonding domains around the central atom. And you can see on the picture there that there's 120 degrees between each atom. So I do want to remember that. So again, just for trigonal planar, 120 degrees between each of the atoms. And I forgot to mention in linear, it's 180 degrees between the atoms. And again, that's always the outside atoms. Okay, so there's 180 degrees between the oxygens, and over here, 120 degrees between the oxygens and the hydrogen, or the oxygen and the hydrogens. Okay, trigonal planar bent, so you can just call it bent. This one has 2 bonding domains and 1 lone pair. It also has a bond angle of 120. Okay. Tetrahedral has 4 bonding domains and no lone pairs. So there's an example there with CH4, and then there is 109.5 degrees between each of the hydrogens. Then we have tetrahedral trigonal pyramidal. So this has 3 bonding domains and 1 lone pair. And again, it has a 109.5 degrees between the hydrogens there. And then we have tetrahedral bent. So this has 2 lone pairs and 2 bonding domains on the central atom. So there's water. Okay, and again, 109.5 degree bond angle between the hydrogens. Okay, so I'm going to give you a few examples before we move on. So in problem number 5, it says determine the geometry for the molecules in problem 3. So I will put all the answers for 3, 4, and 5 on Canvas, but I'm just going to draw some of the examples here. So let's start out with, let's do this one. So SCl2. Okay, SCl2, after I get done drawing the Lewis dot structure, looks like this. So on the central atom, on S, we have 4 bonding domains. We have 2 lone pairs and 2 bonding domains. So coming back to that, so that is tetrahedral bent. Okay, so it has 2 bonding, 2 lone pairs. So after we draw the Lewis dot structure, we're able to figure out what the geometry is. So bent. Okay, let's do one we've already drawn, SO2. So we know the Lewis dot structure looks like this. Okay, so we have 3 total bonding domains on sulfur. We have 3 domains, on sulfur. We have 2 bonding domains and 1 lone pair. So let's go back to our notes here. So it's not that one, right? Because that has 3 bonding domains and a lone pair. So we want just 2 bonding domains and 1 lone pair. So there it is. It's trigonal planar bent. So you have to be careful because there's 2 with the same name. So this one is bent also, but the difference between the 2 is the bond angle. So this bent, the bond angle is 109.5, and in this bent, the bond angle is 120. Okay, let's do this one, PH3. Okay, so there's the Lewis dot structure. So we have 3 bonding domains and 1 lone pair. So come back to our notes here. So we're looking for 3 bonding domains and 1 lone pair. That's not it. This is it right here. Trigonal pyramidal. Trigonal pyramidal. So always draw the Lewis dot structure first. Look at what is around the central atom, how many bonding pairs, how many lone pairs do you have, And based on that, we can figure out what is the geometry of the molecule. In this slide, it just gives all of that information. So everything from the slides previously is all found right here. You don't have to worry about the electron geometry. I really just want you to know the molecular geometry, which is what we just talked about. And I also want you to know the bond angles of each of those geometries. So this just summarizes everything I just talked about.